Welcome to the Happy Maths Hour. Today it's about scale, why scale is so important.
We use it every day of our lives, really, as we walk around, because we have to judge distances and we have to judge sizes in order to move around in our world safely. And the way we do that is comparing the things that we don't recognize and are unfamiliar to us with things that we do know the size of. So if we know the size of one thing we're looking at, and in the same view that we are now taking in front of us or in our rear mirror, we're comparing this surprise thing with something we know. So we're comparing the scale, and that enables us to drive safely or cycle safely or just walk around safely. But scale is used in all sorts of other ways. For example, in giving medicines, we have to be very careful about that. We'll talk about that later, to give exactly the right dosage. And there again, scale comes into it. When somebody designs a road or some machine or a house or a building estate, they make a model of that so that they can study the model and see how everything fits together and exactly how it's going to be constructed. And then they make the real thing once they've got the model right. And then again, there's a scale involved from the model to the real thing. So, and I could go on. I mean, I could fill an hour talking about the uses and the applications of scales in the world around us. But what Caroline has just put up is a picture of 4 baby elephants. My husband and I were on a boat in a river, and we watched on the bank these baby elephants wallowing in the mud and playing around while the adult elephants were sort of socializing, as they do, at the water's edge. And then the leader, as you're always a female elephant, I think so, who's the leader, she obviously gave the signal to go, and these elephants all started off following one another. And here it was just wonderful. My husband was able to take this picture. You can see the adult elephant in the background, so you can compare the babies to the size of the mother, and the smallest one could obviously walk straight underneath the adult elephant there. You can see how small it is, and they're obviously different ages and different sizes. So it gives us a nice attractive picture to relate to scale. We have been doing a series on scale, and today we're going to talk about blowing up balloons and blowing bubbles, which is a speciality of Caroline's. But before we get to the balloons and the bubbles, shall we just recap? Now, some of you may have heard our earlier broadcasts, and some of you this may be your first one. So we'll tell you the story of scale that we've been telling in the last few weeks. Our first week, we talked about paper aeroplanes, which is a lot of fun, and the children will think it's just amazing fun. You don't usually have this much fun in a maths lesson, or maybe you do if you're a good teacher. But the whole point of doing this is that we made the aeroplanes from different sizes of paper, and in fact one huge one that will give you all the links to the videos as well, one huge one which was made with 64 sheets of standard printing paper, which Caroline and Sophie sellotaped together and then made into an aeroplane. But what we see here is we were particularly concentrating on length there, the length of the different aeroplanes, because what we were looking at was these different standard paper, and we did more on the paper, which I'll talk about in a minute. But we were looking about the length scale factor between one aeroplane and the next, and also the area scale factor, because what you do is you either stick two pieces of paper, two A4s together to make an A5, and so on. Oh, there's the big one. Yes. What isn't the big paper aeroplane, but it's the 64 pieces of paper all sellotaped together, or in the process of being sellotaped together. Okay, and you can go down in size as well. You can go from A4 paper, printing paper, folding that in half, so you get half the area, and you go to A5, and then if you fold that in half, you go to A4, and so on. So and also the children can be involved in seeing how far the aeroplane will go. And of course, there's obvious applications to the actual manufacture of aeroplanes, which is hugely expensive. But so the aeronautical engineers make models and test them in wind tunnels before they actually make a real life-size aeroplane. So that was the first week, and then. But it also included the paper sizes. There you see the piles of paper, and you can see how as they get smaller and smaller, we built in that picture, you see a tower built of them, and each of those sizes of paper is half the area of the one next to it, or yes, A4 is next to A5, and A4 is also A5 is half of A4, and A4 is half of A3. Yes, that's right.
Yeah.
But we there looked at the ratio of the areas between those pieces of paper. Okay, the two areas, and what did that tell us when we knew the area was multiplied by 2? What did that tell us about the lengths of the edges? And in that case, there was a magic appearance of this root. Well, not so magic, actually. It's perfectly to be expected. And you look at the maths, √2. So the linear scale factor is √2, and the area scale factor is √2 times √2, which is 2. The area is doubled. Aha! Now this is a tetrahedron in the picture, built with cocktail sticks and some sort of plasticine or blue tack to join them together.
I just wanted to tell you a little bit of the backstory about these images. These images are of a pyramid, and the first time I encountered this pyramid, I got a little bit obsessed with it, because it does scale up or scale down. It's an infinite scaling thing where you just keep, if you keep adding 4 together, you double the length, keep doubling the length, and if you keep halving the length, then you make it smaller and smaller and smaller. And Tony was creating these with the young learners that were coming to visit, to watch us build this huge, giganormous pyramid out of balloons by scaling up as smaller balloons.
Families were coming along. We were giving them toothpicks, and they were making these tetrahedron, as you see there, these Sierpinski tetrahedra, as you see there, and then taking them home. What you've got to imagine is that there's a pyramid, but on a triangular base, right? And then you make 3 of them, and you might make them of balloons. And this was in a shopping mall, and it had to be in a shopping mall because it was too big to fit into a normal building. It was a huge area, huge height. And so you make 3 of these pyramids, and you put them corner to corner, vertex to vertex, and then you put one on top. And so you've made a bigger one, and then you do that again. You take 3 of those, which you have on the ground touching, and then you put one on top. And you keep doing that. And as Caroline said just a few minutes ago, in theory, not in practice, this is where maths is such a wonderful world, because you do such wonderful things in your mind, in your imagination. In your theory, you can go on doing this forever and ever and ever and ever, right up into the sky, and amazing. You can go on forever. But you can also imagine you could go putting these four tetrahedra inside the one that's one step up, going down and keeping going down. And what you're doing with the edge lengths there is halving them. And there are amazing number patterns and geometry patterns involved in that. And then you get something which in mathematics we call a sequence. Say 1, 2, 4, 8, 16. Goes on and on. What would the next one be? Yeah. 32. And we're doubling the numbers each time. And that's what we call a sequence. And that's what happens to the edge lengths of in this construction. And so that's what we did with the Sierpinski tetrahedra, the idea of something going on forever, infinite and infinite sequences, infinite number patterns, infinite geometrical patterns, linking the number and the geometry ideas together. Then we went on, the next week, we went on to make cubes. And Caroline, when she does one of her shows with children and, well, adults are often around too, she asks a question, here's a meter cube made of balloons. It's quite big. How many people can get into it? And it turns out that it's about 25-year-olds, isn't it?
Yes, shall I reveal the picture?
If you've got it.
To reveal. Okay, so
there it is.
These are about 11-year-olds. So we can usually get about 9 11-year-olds, about 24 5-year-olds, and about 12. It depends how much they wriggle. We stop if they're wriggling too much. Fall over.
You see, they have to get inside, so they have to put their heads down, sort of crouch down to get inside.
So for those that are not watching, just listening, a meter is about the length from an adult's end of their fingers to the opposite shoulder, not to the nose. A lot of people think it's to the nose. If you're a very tall person, it might go to your nose. But if you hold one arm out and the other arm go to the shoulder that is adjacent to the other arm. So put your left hand out, put your right hand touching your right shoulder. That is about a meter, give or take. So this cube is that long on every edge length. So it's a big box of that edge length.
It's a meter by a meter by a meter, which is actually 100 centimeters by 100 centimeters by 100 centimeters. And I mean, putting people or letting people crowd inside is just a bit of fun. But more seriously, the maths there is all about scale, volume, and capacity. And the little we also made, or Caroline made, a little tiny 1 centimeter by 1 centimeter by 1 centimeter cube, and a 10 centimeter by 10 centimeter by 10 centimeter cube.
So again, for the listeners, if you just look at the tip of your pinky, just where the nail is, so if you just from the nail up, that is about 1 centimeter cube. For an average size female, at least, that for a man it can be a lot bigger and a child can be smaller, but for an average size woman, that is about 1 centimeter cube, the tip of your pinky above the nail, from the nail up. And then for the 10 centimeter, well, it's 10 times that, but that would be about it's a little, if the size of your hands, if you hold your hands out, and bend your fingers from the knuckle down. I mean, let me just, for those that are watching, let me just remove that. If you, from your base of your palm to, if you bend your fingers over and then join them together, that is about 10. Now you can put your thumb down, your thumbs together as well. That is about more or less 10 centimeters cubed. It's very more or less, but it gives you an idea.
Well, what we talked about then when we were doing that was cooking. Now, what could be more important to everybody than food and drink? Well, okay, petrol for your cars too. It's that we measure liters of liquid, and we also measure grams and kilograms when we measure mass and weight, and we use these quantities in cooking recipes. And recipes, we often, for catering for a larger number, we have to scale up the the amounts in our recipes. So to get an idea of Caroline described these lengths of 1 meter and 1 centimeter and 10 centimeters. And then what we want you to imagine cubes of those dimensions, and then imagine filling those cubes with water. And if you have the 10 by 10 by 10 cube, then it's 1,000 milliliters or 1,000 cubic centimeters, which is in capacity, that's 1,000 milliliters or 1 liter. So when you buy a liter of petrol or measure a liter of some liquid to mix with something, mixing cement or mixing into a recipe, or buying a bottle of milk, we measure that in liters. And so that week we were talking about scale, volume, and capacity, and I mentioned earlier applying that to cooking and to medicine. Now, we also somebody had this flight of fancy and asked this question, and then I put it up on the AIMSEC Facebook page, and we can give you a link to that, about supposing you had this crazy question: what's the weight of seawater, all the seawater on Earth, all the oceans and the seas, and what's the weight of water? Now, we've got a precise measure of 1 liter is 1,000 cubic centimeters or 1,000 milliliters of water at 4 degrees centigrade, and seawater is a little bit different to that, but not very different. So we just took a liberty with that and assumed that 1 liter of seawater was roughly, 1 liter would be 1,000 cubic centimeters, which would have a mass of 1 kilogram. And but the point of doing that was we got some very big numbers out of that. And we talked about millions and billions and trillions, but they're very dangerous words because they mean billions and trillions those words mean different things in different countries. So I'd prefer to work so everybody's sure what you're talking about, in talking about whether you're talking about 1 billion as 1,000 million, as we do on the small scale for these big numbers. Sounds a bit funny to say small scale, but that is 1,000 million, or is it 1,000,000 million? That's what they call the big scale. And people very confusingly in different countries use the word billion to mean something different. The last half hour, we've been talking about scale, and we've been talking about measuring lengths and areas and volumes in the metric system and judging distances. And this is very important in many ways in real life, and using these metric measures. And if we can estimate roughly a distance or a mass of something, or how much what the capacity is in liters, then that's quite a useful skill to have. And that's the point of doing all this in school, that they really understand what these measures are all about and can use them. Now, what we're going to do with the blowing up the balloon and the blowing bubbles is to assume, taking a bit of a liberty here, but we're going to assume that we're making something spherical. That is like a sphere, a balloon is more or less a sphere, and a bubble, because of the surface tension, will usually form a proper sphere if it has time to do so before it pops.
In a perfect environment, a bubble is a perfect sphere. It's the one thing that naturally makes a perfect sphere, and it's the water content, not the soap. that makes the sphere.
So we've looked at different shapes, we've looked at cubes, and we've looked at the Sierpinski tetrahedron, and we've made paper aeroplanes. And now Caroline is going to show us balloons first.
Yes, balloons first. I'll stay dry. We'll leave the getting wet till later. So what's your choice? This one
Let's
or this
have
one?
red, Caroline.
We'll have the red. Right, I'll use the contrast at the back. Okay, so give me instructions, Tony. What am I doing?
Well, Caroline's going to blow up this balloon.
I hope not. That's going to make an awfully big noise.
No, not inflate it fully. You're going to blow what? One air pump full into it.
Yeah, one air pump. Here we go. That's one. I'm going to measure it using the chairs to that is obviously it's not perfect, but that is just about sliding through, so I'm not distorting the balloon, so I'm actually measuring the balloon rather than squishing it through.
When she measures the distance between the chairs, she's measuring the diameter of this sphere,
which is about 9.5 centimeters.
Ooh!
Do you want me to make it 10, or should we just call it 10? This is not exact maths and science here. This is applied mathematics.
Now,
very much.
The question we have for everybody is that she only put one of her pumpfuls of air into it. Now, supposing she now does not one, but she now does 7 more to make 8 altogether. What do you think will happen? So Caroline is going to do, she's already got 1 pump full in there. Now she's going to...
We'll call it 10 centimeters. We're going to call it 10. So what is the new diameter going to be when I put...
We're all together. She's going to scale up the volume by 10. And
I'm going to start again. Instead of 1 pump, I'm going to put 8 pumps in. So I'm going to... It's not by 10, Tony. It's 8, isn't it?
Oh, yeah. Well, no.
Instead of 1 pump, I'm putting 8 pumps in.
Yes. All right. So we're going to scale. It's right. We're going to scale up. Sorry, I misspoke. We're going to scale up the volume by 8.
By 8. And we're going to see what happens to the diameter. And here we go. 1, 2, 3, 4, 5, 6, 7, 8.
Okay. Now, how big is it now? What has happened to the volume is the question that we can answer that question if you think about it, because there's been 8 pumpfuls rather than 1 pumpful. So the air inside is 8 times the volume. Now, what's happened to the diameter? Caroline's going to measure the diameter.
So the diameter is basically the width. That's just about right there. Let's see. So how big?
What do you think the diameter will be of this sphere? The distance between the chairs is...
So with 1 pump, it was 10 centimeters. What is it? Approximately to the nearest centimeter, it was 10 centimeters. So we were rounding. So now to the nearest centimeter, what is the diameter? With 8 times the volume, 8 times as much air, what is the new diameter? That with 1 pump it was 10 centimeters. With 2 pumps it is...
With 8 pumps it is...
Thank you. With 8 pumps. Thank you, Tony. I was kind of giving the game away there, wasn't I, Tony?
We haven't... No, the volume has increased by a scale factor of 8. And Caroline, are you going to tell us what you measured just now?
20 centimeters. It has doubled.
Yes. So the length doubles and the volume multiplies by 8. Okay.
Yeah.
What we found with the paper was the area multiplied by... Very good voice there, Caroline. The area multiplied by 4 and the volume multiplied by 8. Now, are you going to show us your super big balloon or not? Aha.
So if we're very lucky, it's still inflated. I was having a bit of difficulty.
Caroline has got a super big balloon.
That will be a yes. but I've got to move the chairs away. It was, I had to dig up a new method of holding it closed.
It's a meter across.
Chairs have moved away. Now, how's that? Da 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 da. Ah! We're gonna have a disaster. The whole studio's gonna end up on the floor. Ah, here we go. What's we need some sci-fi music. Do 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 do. Can you see it? Do 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 do. Whoa, that's it.
It's so big.
It's so big. It fills up the whole screen. Shall I just let some air out? Hello. No. That gives you an idea how big it is.
No. Well,
see, I've got a picture of the world on it. 1 meter diameter.
And so, now it's going to take how many pumps to actually fill it?
So it was 8 pumps to double it. It was 8 pumps to make it 20 centimeters in diameter. So how many pumps will it take to get to 100 centimeters in diameter?
That's 5 times 20, right?
Yes.
So what's going to happen? It's going to be 5 times 5 times 5, which is 125. Okay. Times your 8, which is so we're going to have to put in 8 pumpfuls of air 125 times. And as you can imagine, Caroline's not going to do that while we all wait and watch. And
I'm really glad I didn't have to do that by hand.
No, she has got an electric pump, and that's how she pumped it up. I'll let you into the secret.
Yeah.
What we're going to show you is doing soap bubbles now. And of course, all you need is a piece of string and some water and washing up liquid to make a solution. And Caroline is showing you just her piece of string, and she's going to there you go. Caroline, are you going to make a small bubble first that's half that?
So this is a meter string. I've tied the knot so that the loop is 1 meter in length, and I'm going to halve it, so that'll be 50 centimeters. It'll be a 50 centimeter loop, and then I'm going to halve it again, so it'll be a 25 centimeter loop, and then I'm actually going to halve it again, so we'll have a 12.5 centimeter loop, and we're going to see how big the bubbles are. Now, the science of the bubbles, creating the bubbles using string, is a little bit different to the science of a balloon, because with the balloon we can be very precise about how much air we put, fairly precise about how much air we put in it. 1 pump on the balloon is pretty predictable. It repeats itself. It's the same amount each time. With this, the amount of air that goes inside the bubble is going to be slightly different. So again, it's not exact, but it will demonstrate it nicely using the amazing soap bubbles.
What we measured with the balloon was between the chairs. We measured the distance across if you were going to go through the middle of the sphere. Here, we're measuring the distance round the outside of the sphere. And if you imagine the Earth as a sphere, this is like going around the equator. And that's what the string is going to form. When the bubble grows inside it, the science of it is all about surface tension. And the bubble will take the form of a sphere, and the string will be around the widest part of the sphere, like the equator on the Earth. And Caroline's about to dip her string. She's got rubber gloves on. She's about to dip her loop of string into the bubbly water, bubbly solution.
12.5 centimeters.
Right, and it's going in, and now she's going to blow a bubble.
I'm actually going to literally blow this one. So that's a little bit bigger, as you can see. You can blow lots of air in, and it makes it much bigger than the circumference. So those two don't compare, which is why I'm not going to blow them. I'm and it's very hard to do with such a small hole. So we're going to actually start with the 25 centimeter one. I just wanted to demonstrate what happens when you apply air pressure to bubbles. They can make, they're very flexible. They have a lot of give, so they
escape from the string and get bigger.
Yeah, they do. So here this one is going to be more, more repeatable, because I'm just more or less putting the same amount of air in each time. So if you can see that.
And Caroline's just blown it off her. She had it on her hand, and now she's blown it off her hand very gently, so it's floating in the air.
And they're getting smaller because as I touch them, the little bits of bubble come off. So I'm going to just do it one more time. Hold it upside down there. That looks more like, you can see it better there.
Right. So now what you're seeing there is a bubble, which is a perfect sphere, and the distance around the widest part of it is what the string was, and she's going to double that length and make a bigger bubble.
So I'm now, instead of 25 centimeters, we've now got a 50 centimeter circumference.
Oh yeah, it's round the, as it were, the equator of the sphere.
We might show you, make it circular so you can see that's hopefully how big the bubble will be. Not bad.
Okay.
So this one, I have to use both my hands to hold it.
It's much bigger. The length is only doubling, but the volume is multiplying by 8 again, because if the length doubles, the area multiplies by 4 and the volume multiplies by 8.
The last one was 50 centimeters.
This is going to be a meter.
1 meter loop. Do my best to make it circular. It's kind of hard to do.
But it will take a circular form of its own accord. Once it gets air inside it, it'll make a spherical balloon.
That's what bubbles do. That's exactly, naturally bubbles make a spherical shape if they're completely free.
They'll make a spherical shape.
If they're free of all forces, they would just be perfect spheres. Oh, here it comes.
There you are, and she's got it on her hand. Okay. Okay. So I think we can imagine it, Caroline. I mean, it's beautiful and it's a lot of fun for the children, but they won't forget these the metric measurements and the scaling factors. And similarity is what we often talk about in maths. And what we mean there is not just similar as we use the word in the English language. It's very precise in maths. It changes in every respect by the same scale, and then it's similar. Angles stay the same, but lengths double perhaps, or multiply by some other factor, and areas you square the linear scale factor and you multiply the scale factor by itself and by itself again, and so you cube it to get the volume scale factor.
So if it's in maths, when you talk about a similar shape, it has to be to scale. Yes. It can be larger, it can be smaller, it can be rotated, it can have a completely different way round, but it has to be the same shape and to scale.
Exactly.
So the angles stay the same, but it doesn't matter if it's upside down or roundabout, as long as the shape is the same, and the size can be different as long as it's exactly to scale.
Now, what was
similar? So it's not like you say you use that word in English. That word doesn't really mean that at all in English. So, but in maths, it's a very precise word. Thank you. I just wanted to get super clear on that.
So what we're doing here is to romp through all these ideas, but we're trying to suggest to you that you and children that you either teach or your children at home, you do some of these things like making paper aeroplanes or blowing bubbles, or looking at the paper if you've got printing paper and folding it again to decrease the scale. And you look at, you maybe make a cube. All the sorts of things that we've been doing won't cost you anything at all, because we've not been talking about expensive equipment or materials to use. And it will take time, and we don't expect anybody to have grasped all these ideas today. Unless they already knew all about them, they could probably teach us. But we've just tried to give you an idea of how you can learn a lot by doing something enjoyable. And you can do it at home or you can do it in school. And teachers are very anxious about teaching everything they're supposed to teach. But I think we've shown the teachers that the syllabus or curriculum, you're going to have covered a lot of ideas in doing these sorts of experiments and investigations, and the sort of activities that children can do in pairs or small groups.
So thank you very much, and we will see you same time next week. Thank you very much. Thank you, Tony.
Goodbye, everybody.
Goodbye.
For greater understanding and enjoyment of mathematics, the Maths Toys YouTube channel is brought to you by AIMSEC and the Aiming High website. In the description, you will find a link to our home learning guide for ages 4 to 18 and a teacher resource pack. If you find this video useful, there is a GoFundMe link in the description to donate to and support AIMSEC. The money goes to bursaries for professional development for teachers in disadvantaged communities around the world. Subscribe, comment and ding the notification bell to make sure you don't miss our latest